There's another type of calorimetry that we do that we often call coffee cup calorimetry. This is at constant pressure. The main time that we want to do this is if the reaction or phase change that's taking place is in solution, or maybe you're trying to measure the heat that's produced when you dissolve something, or the heat that's absorbed when you dissolve something. So if we're talking about reaction or phase change or physical change that involves substances being mixed together in a liquid, like water, we often will use this form of calorimetry. There are some significant differences you need to make sure that you're aware of. In this case, the system, which is the reagents, the reactants involved in the reaction or in the phase change, and the surroundings, which is the water, the spectator ions, all of that, they're in the same container. So with the bomb calorimeter, they're in separate containers, and the heat is transferred from one to the other, and we're only measuring the surroundings. In this case, the system and the surroundings are in the same container. The system is at the molecular level. The surroundings is everything that is inside the container, and we actually have to include the reactants in the mass of the surroundings. So when we're calculating the heat of surroundings with MC delta T, the mass used will be the total mass inside the calorimeter. It includes the mass of the system and the mass of the surroundings. That's the difference. This time, the system and surroundings are in the same container, so the mass has to include both of them. We're going to work through an example problem. If you feel like you can figure it out on your own, you can try it as you go and just check your work. Example number 1, inside a coffee cup calorimeter, and by the way, this is a picture of it. You've got a thermometer submerged in the solution, and then we do some sort of reaction in here. Then we have something to stir it to make the reaction happen. Inside a coffee cup calorimeter, we have a 2.50 gram sample of NaOH being dissolved in 50.0 grams of water. The temperature of the solution increases from 25.0 grams to 37.6, from 25.0 degrees Celsius to 37.6 degrees Celsius. Calculate the enthalpy of the solution of NaOH in terms of kilojoules per mole of sodium hydroxide. We want to assume that the specific heat of the solution is 4.18 joules per gram degree Celsius. We can make that assumption, and that's going to help us in solving the problem. It tells us to write the balanced equation showing the dissolving of sodium hydroxide. Well, part A, sodium hydroxide is a strong base, so we end up with NaOH, and it dissolves. It was a solid. Now it's going to dissolve to break up into Na plus ions, an aqueous solution, plus OH minus ions, inaqueous solution. I also know that since this is a calorimetry experiment, I'm most likely going to be concerned with delta H of the reaction. And I'm looking for that. I'm looking for the delta H of a reaction in terms of, it says right here, I'm looking for delta H in terms of kilojoules per mole. Okay, part B says calculate the amount of heat absorbed by the solution in the cup. So part B, we're looking for heat, Q, absorbed by the solution in the cup. So we need to think about what is the solution in the cup, because we need to know the mass, we need to know the specific heat, and we need to know the delta T. We said that we can assume that the specific heat of the solution is 4.18. The mass, remember, because everything's mixed together, we need to add the mass of the sodium hydroxide and the mass of the water. We're going to add both of those together to get our mass. And then we've got a temperature change. The temperature of the solution is an increase in temperature from 25.0 to 37.6 degrees Celsius. So when I go to calculate this, I end up with, of course this is for the surroundings, the mass is going to be 2.50 plus 50.0. C, 4.18 degrees Celsius. And then delta T is going to be 37.6 minus 25.0. If you use parentheses correctly, you could do that all in your calculator in one step. And end up with Q equals 2765.07, which is about equal to 2,770 joules. After we cancel out grams and degrees Celsius, we would just be left with joules. Now, if you didn't get the same answer as me when you worked through this, you might want to go ahead and follow your order of operations, do your addition that's in parentheses first, and your subtraction that's in parentheses first, and then go back and see if you get the same answer. All right, that's the heat that was absorbed by the surroundings. Part C asks me for the heat released by the dissolution of 2.50 grams of NaOH. It's the same amount, but it's the negative. So Q of the system equals the negative Q of surroundings. So that equals negative 2770 joules. Now we just need to find one more thing. Part D, enthalpy of solution of sodium hydroxide in kilojoules per mole. So we're looking for the number of kilojoules that are produced by 1 mole of sodium hydroxide. So we had 2.50 moles, or 2.50 grams of sodium hydroxide. We want to convert that into moles using the molar mass. Molar mass of sodium hydroxide is 39.998. And when you do that, you end up with 0.0625 moles. Of NaOH. Our heat is given here in joules. We want to convert it to kilojoules because we're looking for kilojoules per mole. So we end up with Q of the system equals negative 2770 joules equals negative 2.77 kilojoules. We want to find kilojoules per mole. It's really going to be that number divided by 0.625. But to do it in the stoichiometric method, we have 0.0625 moles of NaOH. If we looked at our equation, we'd see the coefficient for NaOH is 1, so we have 1 mole of NaOH. I know the amount of energy produced by 0.0625. The amount of energy produced by 0.0625 is negative 2.77 kilojoules. That's my known. My unknown is the amount of kilojoules that's produced by 1 mole. So we rearrange and solve for x. X equals negative 44.3 kilojoules, which means that delta H is negative 44.3 kilojoules per mole of reaction. That's our answer we're looking for in part D. Okay, that's going to wrap it up for today. There's one more example problem, example 2. It's another coffee calorimeter example. You may want to try to work on this. We're probably going to start with that as a warm-up during the beginning of next class.